All right. We left off when we were talking about the value of g. Okay, we talked about how they had a object of known mass, and they would balance it and find out what its weight was, okay, or the force of gravity on it. Then they rolled this big 6-ton ball underneath it and saw how much that increased the pull of gravity, and therefore how much weight it took to balance it over here. Now they knew the mass of this ball, the mass of that ball. They knew the distance between them, the center of their gravities, or center of their mass. So they knew mass 1 times mass 2 divided by d squared. They knew how much the force of gravity acting on it was, and because of that, they could calculate the g value. They knew everything else except that. And when they came out with g, it was 6.67 times 10 to the negative 11. Now, the units over here are not really important, other than the fact just to know that when you plug it in this formula, it will cancel out so that your unit for the force of gravity will be newtons. That's really all that really matters from that. And I'm really not so much worried about 6.67, but know that it's 10 to the 11th. That's 0.000 10 667 at the end. Very, very small. So we say that gravity is a very, very small force, a very weak force. It's a very weak force. And so whatever the mass is, and then divided by the distance, then you multiply by this extremely small number. Whereas like pi, you multiply by 3. So the circumference is 3 times as much. Well, now it's going to be a much, very, 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 very small fraction of the masses divided by the product of the masses divided by the distance. So it's going to be a very small and fairly weak force, only because the Earth is very large that we can even really feel that. Okay. So one of the things that they did this in about the 1700s. Now one of the things is once you know g, now say I know my mass, I know how far I am from the center of the Earth because they knew the diameter of the Earth, so they could calculate the distance to the center of the Earth. We know g, and we know the force of gravity acting on me, and the force of gravity from me acting on the Earth. Okay, we know this answer. The only thing we don't know then is the mass of the Earth. We could plug that in as our second mass and solve for that. Okay, and if we do that, it's 6 times 10 to the 24 kilograms. That would be 24 zeros after the 6 kilograms. And so that's basically 3 zeros would be thousands, 6 zeros would be millions, 9 zeros would be billions, and 12 would be trillions, and that's only halfway to where we're at. So we're talking the Earth is extremely large relative compared to everything on the Earth, and that's why even though gravity is a very weak force, this mass is so big that we can still feel that force. But into small objects, it wouldn't make much difference. Okay, it's only because of the size of the Earth that we can do that. In this day, finding the mass of the Earth was a very big front page news on the papers, and really kind of impressive that we knew the mass of the Earth, even though we had not even discovered many, many parts of its surface yet. We'd like to talk about projectile motion. And basically, a projectile is just any object that has been released or projected by something. It could be a gun, a cannonball. You could release it from your hand like a bowling ball or a baseball. Any object that's released like that or projected, and then it continues to move on its own. That is called a projectile. Okay, so it's very simple. If we want to do a very simple projectile, we could just do dropping a rock. You release it, and it continues to move on its own. Okay, now a couple things to think about it. We know that its acceleration rate is the same. Gravity is going to pull it at 9.8 meters per second squared, or 10 meters per second squared, basically. So after 1 second, it would be going 10 meters per second. After 2 seconds, it would be going 20 meters per second, and 30 meters per second, and 40 meters per second. That means the speed is increasing at all along the way. So in between each second, you will notice that it covers a larger distance, okay? And that's because your average speed is increasing. You're going faster. You're accelerating, going faster and faster, until, of course, eventually we reach terminal velocity. But in this case, that never happens before it hits the ground. All right? So basically, the distance continues. Now, if I were to throw this rock outward, rather than just dropping it, as I did in this case, now we have two types of motion. We have horizontal motion as well as the vertical motion, up and down. Okay? But the thing is, they do not change each other. Okay? Notice after 1 second, it's here. After 2 seconds, it's here. 3 seconds, here. 4 seconds, here. Noticing that it is not getting farther apart because it's not accelerating horizontally. Okay? It's only accelerating due to gravity, and that's going to be down underneath. Okay? Now, After 1 second, over here we said it fell a certain distance. Let me try to get these about the same size so we can kind of make them comparable to each other. Okay, after 1 second, it would have fallen this far. Okay, well, after 1 second here, it would also have fallen the same distance because the acceleration is still 10 newtons, whatever. So after 1 second, it would have fallen here. And after 2 seconds, it would have fallen farther because it's speeding up, down, or vertically. After 3, it would have speeded up because it's down here. I probably should have messed up number 2. Probably should have been down right there. But anyhow, and finally, after 4 seconds, it's still going to go down. So it's still falling at the same rate, but it's also moving vertically. So instead of a nice straight line or a straight line going up and down, what we'd actually get with gravity is we're going to get a line that curves, and it would go down something like that. Okay, and so this curved shape is called a parabola, which you've seen when you graph things on geometry and stuff like that. But it's the path, the actual path that the rock took is called its trajectory. So when we talk about the path of a rocket or of a bullet or of, in this case, the rock, it would be a trajectory, and the path of it would be some type of parabola or curved shape. Okay. Up here we can see an example. This is basically where they did what we just talked about, and basically that's what you can see, that as it goes horizontally, it's still falling at the same rate vertically. Okay. If you threw it down, here's an example where they actually threw a rock down, so instead of horizontally, now that's added to your, besides the acceleration of gravity, you also have some of this force pushing it down. So you notice that it follows a deeper distance vertically, as it still continues to go, has a horizontal component to it also. Okay, and so basically all projectiles are going to show that basic pattern. We're going to have both the horizontal and a vertical component, which will change at different times. Let me just get these out of the way for just a second. Let's look at this one here. Okay, this is just generally showing that if you throw something up in the air, okay, as you throw it up, there's a vertical component and there's a horizontal component, so it gives a curved path in between. Notice as it goes up, what happens to the vertical component? It's losing kinetic energy, so that becomes smaller until it reaches the top, in which at the very top there is no continuing vertical. Once you get over the top, then it begins to increase as it speeds up, going back down, acceleration. So gravity is working against it here. It's decelerating it vertically. And then once it gets over here, then it begins to increase the acceleration vertically back down toward the ground. So you notice the arrows there start getting bigger. Notice that the horizontal arrows stay the same. Now, in real life, once again, there'd be air resistance, and so they would not stay exactly the same, but they would basically, there's not going to be as much change on it as whereas the gravity is affecting the vertical acceleration, either slowing it down on the way up or speeding it up on the way down. But in real life, the actual path of a projectile, here would be the ideal perfect parabola, okay, shape or trajectory. If you shape of the trajectory, if there were no air resistance, okay, if you were someplace like the moon where there is no air, okay, but in fact it would actually go something like this and then curve down quickly here, okay, because air resistance is going to stop, especially, you notice it's horizontal motion, but it's also going to impede its vertical motion, so it's not going to get as high nor as far. And if you were actually shooting cannons or so forth and trying to hit, say, an enemy installation during World War II, they had a lot of big artillery guns and so forth, you would have to take that into account. Now, if I throw an object on the surface, how fast I throw it is going to affect the shape of its trajectory. Okay, it's going to be some kind of parabola no matter what, but it's going to affect the shape. Here we have a person that's 5 feet above the surface of the ground, and they're throwing a ball. If they don't throw it very hard, very fast, it doesn't have much velocity, it's going to fall down pretty quickly, and you have a very sharp curve. As she throws it faster, you'll notice that it's starting to get more flattened of a curve. And if you do it really fast, it takes longer for it to fall those 5 feet. And if it goes far enough, the surface of the Earth begins to curve a little bit. So those 5 meters that it has fallen, it has not quite brought it back down to the surface enough. Now, it turns out that on the average, on the Earth, every 8,000 meters, which is a little more than 8,000 yards, about 1,000 football fields, give or take a little bit, okay, the Earth drops by 5 meters. Okay, so if the Earth drops by 5 meters, if you could make it go fast enough that it would cover 8,000 meters in the length of time it would take gravity to pull it down 5 meters, which is about half a second, a little over half a second, then it actually wouldn't fall, because as it would fall just enough to mimic the Earth's surface. Okay, it would fall at the same rate or amount as the Earth's surface. So let's look at an example of that. If you were on the Earth, if you could throw it where it would go 8,000 meters in the length of time it would fall 5 meters, it would, since the Earth would slope down 5 meters, it would always stay at the same direction above the surface. And it would continue that if it kept that speed up. It would continue that all the way around the Earth until it bonked you on the head as it came around from the other side. Now, can that happen at the Earth's surfaces? No, for a couple of reasons. One, you have air resistance, you have atmosphere. So that would start slowing it down, and therefore it would start coming back down to the ground eventually. Okay? Or the air resistance would heat it up to such an extent that it would just burn up into a crisp. That's why meteorites and things like that from outer space, unless they're very, very large, usually completely burn up in the atmosphere before they reach the Earth's surface. So in the atmosphere, that is not potential. But theoretically, you could do it if you could throw it fast enough and keep it going at 8,000 meters, covering 8,000 meters every time it would have dropped, the time it takes it to drop 5 meters, it would go completely around the Earth and could come around. And that's basically what a satellite is. A satellite is just a projectile that is moving fast enough that, just like the moon, it falls around the Earth because it goes fast enough that it doesn't drop toward the Earth enough that it never really gets closer to the Earth. Now, in order to get that kind of speed, you would have to go 29,000 kilometers per hour, but let's put that into miles. That would be 18,000 miles per hour. So that's very, very fast. And of course, in the Earth's atmosphere, that would just burn it up and incinerate it. But basically, at that speed, so that it covers 8 kilometers per second, then that would become a satellite. In order for a satellite then to be successful, it needs to go 18,000 miles per hour. And it can't go through the atmosphere because it would burn up. So it must be above the Earth's atmosphere, which is about 150 kilometers above the Earth. That would be roughly, let's just say 75 miles above the Earth. So it's got to be above that. Now, it's not above or below the Earth's gravity. It's only above its atmosphere. Okay. Now, the farther it is above the Earth, let's say we have one up here, and when we have another one that's even farther out here, all right, what's keeping them from being pulled into the Earth is their velocity. We'll call their, I can never pronounce it, but they're going at a tangent. Their velocity is at tangential, but anyhow, it means going at a tangent. Their speed going this direction, and the Earth is pulling it toward, and that's what makes it curve around. If it's going too fast, it will just keep right on going and pull away from the Earth. Okay, if it's going too slow, it would eventually start getting pulled closer and closer to the Earth and eventually crash into it. So basically, their velocity is what keeps them from crashing into the Earth. But that's to overcome the force of gravity. It has to be enough to overcome the force of gravity. But as you get farther from the Earth, what happens to the force of gravity? It gets less. So the farther out away from the Earth a satellite is, the less velocity it needs to stay in orbit. Okay, because there's less gravity pulling on it, so it has to have as much velocity to counteract that. The closer it is to Earth, there's a stronger pull of gravity, so it needs a faster speed to counteract that and keep it on its curved pace.